Great. I'm starting. So this is module number 6 from IASA with Professor Evangelos Gazis. He's my supervisor. And the goal is to provide an introductory knowledge on what is an AI model and how we can train it. I know that in the past days we have had some definitions on what is AI, but allow me to give another perspective. So one of the fathers of AI, John McCarthy, in 1956, he coined the term of AI, and he said it is the science and engineering of making intelligent machines. Okay? Science and engineering of making intelligent machines. But how do you make a machine intelligent? This is the question. We had it, right? We talked about it yesterday. How you can make a machine intelligent? Before, yeah, that's the best way. But I want you to answer another question to me, if you can. Can you tell me how many colors does the flag of South Africa has? Don't Google it.
Four.
7.
Can you tell me now how many colors there are?
Is white and black considered a color?
The flag.
I'm colorblind.
Okay, the majority said 6. I hope everyone said 6. So this is true. So the answer is 6. And let's take a moment and think about what happened here. So I communicated with you through the language system. I asked you how many colors there are, and you communicated with your visual system, and you said your visual system scanned across the picture, you counted the colors, and then you went back to the language system and you told me just seconds ago the answer is 6, right? Until we understand the process of what happened here, we cannot understand human intelligence. It seems simple, but it's not.
It's not the colors.
No, it is. It is. It is.
I thought there was a hidden trick.
No, there is no hidden trick. It's just to explain exactly what we said, that you can actually have intelligent machines, but it's not a straightforward process because intelligence, it's not defined. That's why I don't like definitions of intelligence. So when we talk about intelligent machines, we're trying to explain here. We don't talk about definitions.
There is a language problem of the founder because he understood the intelligent something which is not problem.
No.
Because intelligent is definable in many manners.
You're right about John McCarthy. He said the science and engineering of making intelligent machines, but he was forward thinker and he was trying to address intelligence. It's not that he believed that there is intelligence already. He was just trying to introduce the term intelligence.
Yes, but semantically intelligent.
Semantically
has
correct.
A lot of,
but he was one of the fathers of AI, right?
Yes.
A very distinguished professor.
Correct.
In any case, we can move forward and we can say that when we talk about intelligent machines, we can talk about computer-based systems that are capable of human-like reasoning and decision-making and adaptation. And when we talk about adaptation, we mean interact with the environment. What we did just right now, you were adaptive. I asked you questions. Those of you who were not sleeping after lunch, you answered. And this was adaptation. And it's possible changes using qualitative and quantitative data. Therefore, when we talk, we know that we have AI, it's a broad field. It's a broad field of techniques focusing on these intelligent machines capable of using models to think, perceive, and act. You did that. You thought, you perceived, and you acted. And these techniques are depicted in the following diagram. We've covered several examples the previous days. We had machine learning examples, natural language processing, speech recognition, robotics. I don't think we had robotics, did we have? But anyway, and we also had computer vision. An example of computer vision is the first AI supermarket. So it was built last year, I think, in Emirates. This is the one. You walk inside, you take out of the shelf your products, and you just walk out without waiting in the line, in the cashier, nothing. You just walk out. How does this happen? There are cameras. They recognize your face with computer vision. They recognize the products. They can understand if you take a product and you change your mind and you put it back, and they have your credentials, your bank account pre-recorded in the database, and you just walk out without having to wait in the cashier or anything. So this is an example of what's already happening, which is quite advanced. And another one that we talked about in module 1, I think we said about driverless cars. Showed some videos as well. Most of the kids you will teach, the teachers will teach, will never know how to drive, only for fun, in a few years from now. So the AI have today is that AI, according to the WC, will add 16 trillion to the global economy by 2030. It's very close. And Sundar Pichai, the Google's boss, he said that AI developments are more profound than fire or electricity. Let's take a few minutes just to understand what AI does in healthcare. And let's look at it through the perspective of the impact that it had in treating against the pandemic. The AI algorithm I've talked about several times during the breaks was the first one from MIT, almost 1.5 years ago. And it was able to detect, it took your phone, you coughed, it recorded your coughs, it analyzed it, and it would tell you, do you have COVID or not? The amazing thing was it was able to detect asymptomatic patients with 100% accuracy. This is amazing. We've been trying to do that in our lab the past 6 months. We have some good results, but the thing is, we're introducing other data as well. So we are introducing not only coughs, but also multiple kinds of data, your age, your history, your medical history, your how do you say a sentence? How do you pronounce a sentence? It plays a role in how you have, if you have COVID or not. Imagine what we could do with this tool if we were in the position to take advantage of it at the point that the paper was published. It was very early during the pandemic. Another example is Spot, this little robot dog. I don't know if you can see. It's very cheap, only 74,000. And you can take it as a gift. And it helps to triage patients remotely. So imagine this, my sister is a doctor in US. So in the beginning, they had Trump back then, and she couldn't have a mask. They didn't have protected shoes. They didn't have anything. And she was forced to go and treat COVID patients without protective uniforms. And if they had this little dog, it could go and it could say, okay, analyze temperature with computer vision, your face and everything. And it could say, you have COVID, you can go over there, you can go over there, you have another thing, wait, without risking the safety of the own personnel, the own medical personnel. Another amazing, of course, application for COVID was this, the vaccines. You know, we don't really know that, but the reality is that even the chief officer of Pfizer said that it drew on AI to roll out the vaccine. Did you know that? That we have vaccines due to the use of AI? In our recent publications in the Computational and Structural Biotechnology Journal, with my team, we searched how many models that were released during the pandemic. And there were 101 studies included, and we had 14 models for screening. Screening means the patient comes to the hospital, and with this model, we can, with a model that every group developed, they could say, okay, you belong to this department, or you belong to the ICU. And diagnosis and prognosis, another huge, amazing thing with AI, the prognosis, of course. So it was we found models that could predict the ICU need to go in the intensive care unit, which is the most important thing because the majority of the people that have already died because they entered ICU. So if you can predict if a person enters and when it enters, you can also save days for the doctors to treat. So another thing was ventilator need, mortality risk. They could calculate with the models who was going to die. Severity assessment or hospital length stay, which can be used outside the pandemic as well, of course. This was published last year. Another example in healthcare is mental health care. So predicting depression from social media before you get a formal diagnosis, according to your posts or how you actually react. 20% of US patients struggle with a mental health disorder.
Do you know which tool they use there?
To treat mental health care illness.
To predict the...
To predict, they have developed models based on some kind of specific architectures, in any case, and they could have as an input social media, face recognition, emotion recognition, all that merged together in order to give you a result on whether or not you have depression, you have another disorder.
Was that something new? They didn't do something.
No, yeah, but it was based on known algorithms, okay? It was not fire invented, but it was something new as a setup. And this is amazing because think about every 40 seconds, one person dies from suicide. It's incredible. I mean, we don't only need it for the generation, for the students, if they are unhappy or something. We need it for actual people that die every 40 seconds out of this in the world. So we can, and also parental control. There are a lot of things there to protect. But in this, let's go back. So this was a very brief introduction, to give you just another approach. The learning outcomes of these modules would be just to touch a very high surface, okay? It's not deep knowledge, of course. We cannot gain that in such a short time, but we will have just a glimpse on what is machine learning again, from my perspective, neural networks, some examples of machine learning algorithms, and how to train. So the first part, we can see what it is and how do machines learn. How do machines learn? Can you answer that? How do we learn as babies? Think about a baby, when you were a baby. You learn from examples. Nobody teaches you rules, nobody. Nobody goes to the baby and says, this is how you conjugate verbs. This is the rule one. This is... He listens, she listens, the baby listens, and understands by examples, right? So if you go to school and you want to learn another language, you learn by rules. So there's two things, rules, examples.
But also the structure of your mind helps.
Of course. We all know this game, right? Tic-tac-toe. Triliza in Greek. We've all played this game when we were bored at school, right? Okay. So how do you play this game? How you can teach a computer to play the game? One approach is to go to the computer and say, okay, here are the rules for tic-tac-toe. Tell me one rule. Can anyone tell me one rule? Start in the center. Exactly. Start in the center. Another rule. If you have two X's over here, you have to have a third one, right? Okay. Another rule, if you have to start from here, you can go from here and from here. The choices that you have. Great. In total, there are only 6 rules. Simple, right? 6 rules. You can insert these to the computer, 6 rules, and it can play the game. Okay, where is the intelligence then? The intelligence is on how to teach the machine, not only to play, but to win. And how can the machine do that? With your help. It can do it by rules, or you can give a lot of examples and you can tell the machine, learn. Just look at it and learn from the examples. This is a machine learning approach. You know how many board configurations there are in tic-tac-toe with only 6 rules? 5,400 or something. This is very few for the machine. For us, it's not. What? The board configuration. 5,000. So you can understand that for a human being, it's quite complex, but to the machine, it's just a few milliseconds to do that. And the best way to teach the machine to learn tic-tac-toe, for example, would be to give these examples. One way would be automatic, and one way would be manual. The manual is, okay, I'm giving you all these 5,000 examples. But we are really bored as we human beings are really bored. We don't want to give 5,000. So we say, go and find it online. Or how you can actually teach it. Tell him, play with a copy of yourself. Do a copy of yourself and play with yourself. And stop bothering me and give me the results, right? So this is an example. Think about chess. Somebody mentioned chess. There are not only 6 rules, of course. And this increases the complexity. Summing up, there are 2 ways of teaching the machine to win. Program it by giving it rules or by giving it examples. Do you know what it is? Have you ever seen it? The caterpillar? Okay. In 2004, the US government said, I'm doing a contest and I want to give $2 million to anyone who goes and puts software into a car and drives the car through the desert for 150 miles or something. So researchers signed up, companies, hackers from all over the world, and they were selected 100 research teams, and they said, we're going to try to win the 2 million, right? So the contest started in the desert in California, 100 cars. Who won? How many cars did make it to the finish line? None. Nobody took the 2 million. Nobody. Because every single car fell into the ditch. And why is that? How come we had tools that we could use back then, and with those tools, and I'm talking about MIT, Stanford, Columbia, the top in the world, and they could not find a way to have a driverless car through the desert to make 150 miles. The next year, the contest happened again. And there was a winner called Stanley from the Stanford University, from the Stanford team. They were very stubborn as well to win. But they said, they asked them, how did you manage to overpass everyone else, every research team from last year? And they said, we used machine learning. And instead of trying to program all the rules that there are in driving, we tried to make the machine learn like we teach a human driver to drive. You see? So if you teach the machine how you teach a human, it can learn better sometimes. Therefore, the difference of machine learning and traditional programming is that in traditional programming, you have the rules, you have the data, and then you have as an output the answers. But in machine learning, you have the answers, you can have the data, and then you can create the rules. The goal of machine learning is usually to predict results based on incoming data. And there are some key components in machine learning. So there is the first one, the most fundamental one, we've talked about it, it's data. We have, as I said before, the manual way, the automatic way. And since COVID came, we also have some very positive results to research, because we have a lot of open data opened up. And it's why in Kaggle that Fabio talked before, we have so many open data sources.
Sorry, can I clarify?
Yes, yes.
Can you go back to the figures with the data? Yes, this. Okay. Prolog is something like a second. Oh no.
Prolog can be programmed to do the second. Yeah, it can be.
Because
For AI,
the
basically.
the inference machine that
Yes, exactly. It can be used. It is used, but what we've seen in the other presentation is it is an older approach, let's say.
yes.
So
Do you mean that the TikTok
example
with the examples can produce by default some
better
rules?
results, not some
No,
rules.
no rules. We cannot have
No,
from the
you don't
models.
give it rules. You don't give it rules.
Yes, I
You give us an input, the answers, and you
Yes,
say,
yes.
here it is,
Here that,
and
yes.
here are the data,
and
and then it can create the way to win. This is
this is the rule, the way to win.
yes,
Okay, because
the perspective of the way to win. Yeah, no, you're right.
Okay.
You're right. Definitions can be mixed up.
The idea is that I want to take a photo. But it was nice.
But concerning the data, you can see this here. It's the old way of Google trying to realize if you're a robot or not. You remember the CAPTCHA thing. So for Google, for many years before they had some legal problems, they had as employees all of us. So basically, you were the go to buy something, Google would pop up this, and they would say, choose who is the cat, where is the cat? And you would do what? You would do what we call labeling. You would label and you would say, this is a cat, this is a dog, and so on. And by your tick, your answer, you would work for Google because Google would save your answer, and it had a huge databases with labeled data. One of the most difficult things today is to label data. As much as crazy it seems to you, and it might sound crazy, labeling data is a process that is very needed when you develop the algorithms. And I'm going to talk later on when you develop which algorithms. Another component is features. So you have input data that you want to feed into the machine learning models to learn the parameters and make the predictions about the output. They're also called parameters or independent variables, whoever has known knowledge in statistics, or predictors. Then you have the algorithms, solving different types of problems such as regression, classification, or clustering. I'm going to give you some simple examples to understand what it is. Classifications you understand already, but I don't think you understand the rest ones. Not all of them, at least. The output variable, the dependent one. And this is the variable that we want to predict. For example, if you want to build a mortality model, the output would be, will the person die or not? I hope I don't give too pessimistic examples. So another thing is hyperparameters. Hyperparameters are different from the parameters. This is something that you put in the model initially. You have to predefine it. You have these hyperparameters, and that you need to do it before you train the model. It's very important. Sometimes the reason why it doesn't work is this. Then you have loss or cost function. It can be taught with a lot of mathematics, but in a nutshell, we can say that it's a way of measuring how accurate your model is in the prediction that it makes. Therefore, this, I think we've seen it in another presentation, but basically this is it, that we have to pass the knowledge also to the facilitators and the students that AI is a broader thing, and it involves machine learning, and it involves neural networks. And a subset of this can be deep learning. So everything is a whole field, and you have subfields inside. This is the classical boring problem. Cat or a dog? How you can classify? There is a process. There is a process to do it. So you have the data. You define the task. I want to classify cats from dogs. You collect the data. You design the features. What does feature mean, as we said before? So if it has a relatively small nose to the head, to the size of the head, maybe it's a cat. Or if it has big ears, probably it's a dog. So you design the features and then you train the model. We will see examples. And then you test it to see if what you did is good. Moving on to neural networks. Another very classical example is the human brain. So it's inspired by the neurons on your human brain that actually works for passing on the information through the neurons. Exactly, you can have one input and one output, right? Or you can have multiple inputs and multiple outputs, just as your human brain works. So you can have one signal input and one output. This is how it looks. We shouldn't be scared of it. Majority of you by now are familiar with the picture. So this is a neural network. We have an input layer over here. We have an output layer over here. And in between, there are some hidden layers. Every node is connected to each other, and every string can have a weight according to what it is important or not. Let's say we want to distinguish what is this differentiated shapes, a square, triangle, or a star. We import it to the neural network. There's some work doing here. So there are some called activation functions. So the activation functions are used to activate some of these nodes. And with some math behind it, you conclude to these three outputs. You conclude if it is a square, it gives you a probability that the result is a square. Let's say 0.5, a probability that it is a triangle, and a probability that it is a star. It's completely crapping this one because it is 0.5. So it means it's randomly, predicts randomly. So it's not a good model. Okay. There are several types of neural networks. We are going to give some non-exhaustive examples. The very well-known convolutional neural network, or CNN, it's good for image recognition, as we've seen. Recurrent neural networks and long short-term memory. The recurrent are good for sequential data, for example, language translation, and the LSTM are good for speech recognition. We've seen very good examples with Yanni's tool before for CNN. This what we were seeing before with the if it detects or not this and that and everything in the road was basically CNN, convolutional neural networks, because they are used in cases that we have pictures and videos. They have good accuracy. Then we have recurrent neural networks for speech recognition or voice synthesis in sequential data, as we said before. And an example that you can teach the students with hands-on experience, but on a lower level, or even in higher level, but okay, it's a game more for smaller kids, it's this one. So you say, take cups, plastic cups or whatever, and put some decisions here. So you have the data, the input data, which is the games, and you want to distinguish the red little games. So the target is this, the output. Place the cups like this, create some kind of slopes, and say, is it round? Yes, go there. If it's not, go here. Is it bigger than this? Yes, go there. If it's not, go here. And then you end up with a target. Maybe you should do that to tidy up the room. So moving on to some examples of machine learning, a little bit deeper, but not too deep again. We have two types, as we said, of data, labeled one and unlabeled data. So in unlabeled data, we used unsupervised learning. And in labeled data, the goal is to predict, and we use supervised learning. So this is the difference between supervised and unsupervised learning. This is the difference. In one case, you have labeled data. This is a cat, this is a dog, this is a square, this is a triangle, a star. And then on the other case, you have unlabeled data. This is considered the black box of AI. And in every case, you have different types of problems to solve. Here are some names just to hear them, just to get familiarized with the names, and we can say a few examples later. So we have linear regression. decision trees, we've already said some examples. K-nearest neighbors, random forest, kernel methods, deep neural networks. And what it shows here, it's something that I wish I had time to introduce, but I can't. Interpretability, which is a huge research field now in AI, meaning that you have to find ways to explain how you develop the algorithms for a lot of serious reasons. If we have time, we can talk later on. And here's the performance of the algorithms, these algorithms. And you can see that the more we move to more accurate algorithms, the less interpretable there are. In supervised learning, we have usually two kinds of problems. We have classification and regression. So classification we've seen already, it's very simple to choose an object category. Regression is to predict a specific point. And let's see an example. So in classification, we basically split the objects based on an attribute that you know before, that the apple is red, or this fruit is green, or I don't know, whatever you may have in your hands. This is to classify, and it's used for spam filtering, for language detection, for sentiment analysis, for recognition of the handwritten characters that Maria said before, for fraud detection. And you have some names of popular algorithms over here. For regression, regression is basically classification where we forecast a number instead of a category. And it's used for stock price forecasts, for medical diagnosis, for correlations, and so on and so forth. A decision tree. So if you go to the bank and you ask a loan, they can use a decision tree algorithm, not so simple, of course, to decide whether they would give you a loan or not. So your credit history, is it bad or good? Let's go this most usual one. So do you have a pledge? Yes or no? Do you have a guarantee? Yes or no? So I'm not going to give you, or I am going to give you. In unsupervised learning, though, the problems that you are demanded to solve is, for example, clustering, clusters. So it divides the object based on unknown features, features you don't know. You have a bucket of objects and you don't know the features. Nowadays, it's used for market segmentation, to merge close points on a map in Google Map when you have restaurants and they merge it closely together, for image compression as well. Moving on to reinforcement learning, just to have an idea of what it is. Reinforcement learning is used in cases when the problem is not related to the data itself, but you have an environment to live in, okay? It's the game that you play, the environment, or it is the desert, in the desert. So there are some approaches that use reinforcement learning to solve this kind of problem. And the goal is not, again, to give all the rules, but the goal is to minimize the error, to minimize the possible wrong answers. It's used, of course, for self-driving cars, as we said, for robot vacuums, for games, for automatic trading, enterprise management, and so on. We also have ensemble methods that are used for everything that fits classical problems, classical algorithm approaches, but it works better. And for search system, for computer vision, for object detection. And basically what it means, think about this. If you take a bunch of inefficient algorithms and force them to correct each other's mistakes, this is ensemble. The general principle of model selection is as follows. When you have enough data, you separate them in 3 subsets. The first set is training, then you have tests, and then you have validation. Let's see what it means. So let's supposedly you have some data for the hours that the student has done to study, okay? For the hours of study and the hours of sleep. I would be 0 here. But anyway, so you have all these hours of study and these hours of sleep. And you have a result for the test. Success, success, fail, and so on. If you have this data set, the split of the data set, it can go like this. It's a very common method to split it, like we say 80-20 or 60-40. You take 80% of this data and you use it to train the algorithm, okay? The 80%. And then you leave the rest of the set, 20%, to test. To test if what you trained before is accurate or you have done some major mistakes. There are a bunch of tools that you can use. I have deleted a lot of slides because Fabio ruined my presentation. Had Kaggle. So we can use a lot of models. I don't want to, if we have time, we can see them one by one, but not Kaggle. There are nice examples, or as Yannis showed, on how to introduce a student to an environment where he can go either with code or without coding, without programming anything. If you want to introduce programming, there are several good coding environments. In our lab, we usually, if we don't have money, we use Google Colab. And it's a nice resource because it also gives you mostly 12 gigabytes of RAM. It also gives you graphical processing unit, which is something that you need usually in this stuff. There is also Jupyter Lab if you want to include coding. And moving on to some examples at the end of how you can train, I found recently some very interesting approaches, some papers on how to teach AI, basically what we're trying to build here. And there was this year, just a few months ago, there was a publication by a very good research team is in Johns Hopkins University. They said, they published this, a perspective on K-12 AI education, it's called the paper. And they say that the goal is to design modules for high schools in Baltimore and Kansas City. So they did some research, they had some ideas published. And the thing is that you can have 4, let's say, parts. The 0 part is that you can review all of the background material in the context of solving the problem. Then you can collect and explore. Then you can design and train the model. And lastly, but not least, to provide an application of these models that you develop in the real world, not to lose, as David said, the motivation at the end of his presentation. So this is what they have as an example, and it's a pretty nice thing that we can adapt in our own examples. To predict the weather, for example, to predict the weather. And they said the students learn about climate and weather variables. They train it, the model, based on data of the weather of where they're living currently, let's say. And then they create a web app to connect it with the real world. So the part one, as we said before, is to refresh your background. And they said they learn concepts about the climate, the environment. At each step, they can see how the content they learn will be eventually useful. And then they explore. So they explore and they get familiar with using different visualizations, for example, to make decisions on what to include or what to exclude. They can also pass on to the next part, the training part. As we said before, if you remember, in the neural networks, we had some training data, we had some weights, some activation to predict. And if you had errors, you had to go back to the process and do the same thing again to get an optimum algorithm. But they train the model accordingly, and then they deploy it in a web app. So this is a pretty nice, straightforward process that students can do as a project-based learning. They can build a web app to predict the weather in their city, let's say. Another example is a more advanced, but not so much again. It's about molecular biology. They will learn the flow of the genetic information to DNA and RNA in order to understand how the protein works, how it works. And they would say, we're going to refresh our background. And they are going to have this basic knowledge of how RNA works, how DNA works, how the protein sequence goes. And then they would go and explore the data over here. And they would use open databases to explore the data. And they would say, okay, I have informations concerning the 3D representation. I have nucleic acids. I have complex assemblies. They would move on to the training, of course. And they would say again, I'm going to train. I'm going to put some weights, activate, predict. And then if there's an error, do that again. In this case, they use a supervised learning algorithm. They can use a supervised learning algorithm. And they use the data, the genomics data that they collected to predict the sequence of the protein. And then they can give, this is cool, a real world deliverable. Because the students that can accomplish that will have the option to sequence their DNA. They would take a sample, use their saliva, and they would analyze their saliva, and they would create an AI model to get the proteins coded from their saliva. Another interesting, very recent paper, I think Grigoris would like this one. It's a meta-review of literature on educational approaches for teaching AI in the K-12 in Asia Pacific region. Okay, it's very specific, but it is what we're trying to do. So this meta-review aids the mapping of existing AI curriculum and activities and so on. One approach they propose is the holistic model. It consists of what we're trying to do in this training, of basic AI knowledge, processes, the impact of using it, whether it is relevant to students, teacher-student communication, and technological adaptability for the students. They also propose the use of the TAC, if you can pronounce it like that. It is the technological pedagogical content. Maybe the teachers know about this already, I didn't know. So it's a framework to improve AI teaching and learning in terms of content knowledge and pedagogical knowledge and the merge of these two. And there is also a case study that demonstrates that curriculum planning uses applied self-determination theory and methodologies for the process of learning. As a result, the educators, they conclude that they can consider these three elements to design AI curriculum with appropriate theoretical frameworks. To end this presentation, it would be good if we have time to introduce concepts such as interpretable and explainable AI, as I mentioned before, and of federated learning. It's kind of one of my favorites. I think it's going to be everywhere in a few years in terms of what it's used. No? It's difficult to introduce it in lower levels, though. You need a bit better levels. But the concept behind it is that you don't have data centralized in one places, and you can train the algorithm without actually having to access, let's say, all the databases. It's something that it has a good application in healthcare, and if the hospitals of the future can manage to have it as a technology to apply it, then we can solve a lot of problems in the patient process. We can have huge amount of data without the problem of the data privacy, which is also a major topic that it's going to be covered tomorrow, I think, with module of AI ethics. Who's in ethics tomorrow? It's you?
Professor Kakas.
Okay.
He will be online because he couldn't make it.
Okay. So this is all I wanted to say as a first glimpse on AI models. And just to conclude, from my point of view, it is very important to think about it. It is a great danger that people conclude too early that they understand. So none of us will become expert. None of us is expert. You cannot be experts. I don't know. This is my point of view. And it's very important. Why? Because in education, things are changing so fast the last 50 years or so that you need adaptability, and you need to understand that you cannot understand everything. Okay? That's it. Thank you. Questions? No?
Do you have any experience of doing any activities with students, colleagues, maybe?
Well, with colleagues, no, not so far. But these last papers that I didn't know about, and it was a few months ago this year that they were published, I think it's a pretty good approach to create for us to manual, let's say, on how to create an AI curriculum. You've seen the last two papers? It is very interesting.
Also the links.
Yeah, yeah.
But what I'm suggesting to everyone to do tonight for homework. In the last module tomorrow, besides discussing the learning credibility template, which is already I've just do that. And we'll try to finalize that. I want you, because according to our proposal, every partner needs to produce a minimum of 2 learning and creativity plans in the next few months on certain topics and certain activities related to what we are learning this days, but also to try to make it adaptable to the level of education, work with teachers also, and develop ready-made learning and creativity plans with materials, examples, activities, project based if necessary, etc. etc.
Yeah.
So try to think tonight from what experience we are all getting. I mean, each one of us have their own ideas based on the module you do, but from the other modules we have.
Mhm.
And tomorrow I'm going to share with you during the last module spreadsheet with organizations, partners, and 2 columns to try to at least give it an initial title of a learning and creativity plan. Okay? Initial, which means after 1 week you can change it. Just to have something, because now a lot of things are fresh in our minds, and maybe easier to decide something now, and we see what the others are saying. So not to adapt. Try to think tonight.
So sorry, you mean learning and creativity plans not for each module?
Sorry?
For each module? Not for
Not
each,
necessarily.
not necessary for the modules that we have, okay,
It could be a mixture.
okay.
The modules are helping us to understand things, get ideas, see what is impossible, what's good, what is possible, what we can do, what we cannot do, etc. But we have but to fight the challenge, because it is a challenge. To try to put things in a but otherwise we wouldn't have innovation. This is the innovation. This is what we're going to do because it doesn't exist. We don't have lesson plans how to teach our schools.
We can work with them because we are the second partner at this point.
Yeah, each
So-
party has to produce at least 2.
Yes, yes. So we are going to, because
And
there are
Portugal
similar
also.
You
things
work together,
between-
but you have also.
We were initially
Here,
Yes, of course.
collaborate.
Yes, and this is the reason that I want to
If
collaborate.
you work
with
together,
Maria.
I think you should produce minimum 5.
Minimum 5.
Because there's a momentum if you work through. Instead of 2 each, it would be minimum 5.
Okay,
Κάτι θέλω να σε ρωτήσω, κάτι παρακάτω.
Εδώ, στα paper.
Μετά τα paper,
Μετά τα paper.
Κάτσε να δω λίγο. Αυτό θα σου πω.
Το,
Όχι, όχι.
πριν τα paper.
Πριν τα paper, μόνο. Στο coding. Στο coding. Μπράβο. Εδώ. Θέλω να ξέρεις να σε ρωτήσω εδώ. Εδώ, στο collab, είναι training τα μοντέλα ή κάνεις εσύ το training. Πώς γίνεται εδώ,
Εσύ το
στο
κάνεις.
collab.
Είναι developing environment, το οποίο μπαίνεις μέσα, κάνεις coding κανονικά.
Είναι αυτό που είχε δείξει κάποια στιγμή.
Σου είχα δείξει.
Μου το είχε δείξει αυτό.
Πού όμως, στο Zoom, θα κάνεις Skype. Θυμάμαι.
Κάτι είχαμε κάνει.
Ναι, εκεί, παίζεις στο Colab, έχεις το κώδικα και έχεις και τα αποτελέσματα από το output από κάτω. Δηλαδή κάνεις τον κώδικα εδώ και σου βγάζει το output από κάτω.
Τι σημαίνει το training που σου κάνει, γιατί
Κώδικα.
έχεις examples.
Ναι, έχεις.
Αλλά πρέπει να κάνεις specification και τέτοια πράγματα, ας πούμε, όχι.
Ναι, coding, αλλά έχει και κάποια έτοιμα, pre-trained.
Αυτό, θυμάμαι, το είχαμε πει τότε.
Έχει.
Αυτό. Εκεί μπορούμε να δώσουμε παράδειγμα, άμα δούμε κάτι εκεί πέρα.
Ναι.
Αυτό έχει ενδιαφέρον, να δούμε αν μπορούμε να το κάνουμε. Δηλαδή, για να πάμε στα pre-trained, να δούμε μήπως, καταλαβαίνεις.
Οκ.
Θα είναι ενδιαφέρον να το δούμε. Και επίσης ασχοληθούμε και με το Kaggle.
Το Kaggle μετράει.
Χρησιμοποίησαν τα παιδιά.
Ναι. Αυτό είναι
Είναι
touch.
μια τριεφή. Όχι, δεν είναι touch.
Και πώς πας εκεί.
Κάνεις
να
κλικ,
το.
να κάνεις κάνα κλικ.
Οκ.
Φεύγεις από τη μία οθόνη και πας στην άλλη. Εγώ έχω μπερδευτεί, τέλος πάντων, δεν έχω καταλάβει τι λέει. Το mouse δεν μου έρχεται καθόλου.
Αυτό πρέπει να το δώσω στο παιδί.
Είναι το...
В смисъл, профилът ти е оставен отворен този.
Така ли, аз
Да, да, споко.
А защо отворим профил?
Не знам, ти си го отворил.
Малка си.
Ето, може би не знам.
It just sent now.
Well, this is the last one.
Yes.
When was it sent?
Couple of minutes.
Yes, yes.
Yeah, about 10 minutes ago.
Yes.
Okay.
Ние продължаваме да записваме.
Sorry, did you? Sorry,
Елени?
Eleni? Is the recording stopped? I'm just asking. Okay, yeah. No problem.
No.